In this video, we're going to see how a reaction taking place in solution modifies some of the ways that we deal with stoichiometry for that equation, for that chemical reaction. So our learning goal is going to use concentrations in a solution to, as a means for quantifying the chemical reactions that take place there. So we're going to start by looking at this mole-to-mole conversion table that we discussed in another video. It looks something like this. This is one where we are given moles of one substance, A, and we need to convert it to another substance, moles of another substance, Z. And it involves just one conversion factor, which is basically the mole ratio, moles of Z to moles of A. Now, how is this going to change in a solution? Well, we're going to get rid of some of this, and I'm going to replace it with some other stuff. All right, what have I added on there? Well, now our input may be mils of some kind of solution. All right, and we have to convert those mils first to liters. So that's the first conversion factor. 1 liter is 10 to the third mils. And then we're going to need to use the concentration of the solution to extract from that the moles of our reactant A, because it's going to be in moles of A per liter of solution. So those two things fall under the heading of conversion to moles. So basically this is just a fancy way of saying in order to get the moles to start with in this particular stoichiometry problem, we've got to actually do a little bit of work with the solution and work with the concentration to get to that number of moles. Then we can get to the stoichiometric conversion, which is the mole ratio, moles of Z to moles of A. Now you can see here we can cross things out and show that in fact they are going to cross out all of those units and we'll be left with moles of Z at the end when we're done. The only change in all of this is the conversion of concentration to moles of solute. So let's see how this might work in practice. Let's suppose I have excess methyl bromide added to a 200 ml solution that is 0.2 molar in sodium chloride. So the reaction that's going to take place here is actually a substitution reaction where the chloride is going to substitute for the bromide on the methyl. And we'll end up with methyl chloride and sodium bromide in aqueous solution. So now we want to know how many moles of the methyl chloride are produced. Now ordinarily we'd have to worry about what is the limiting reactant, but whenever you see a problem that says excess of this is added, that's not the limiting reactant. It's the other thing that is the limiting reactant. So whenever someone specifies excess of something, they're trying to tell you that is not the limiting reactant. So we're going to use the amount of sodium chloride now as our limiting reactant to calculate our theoretical yield. The initial moles of sodium chloride we have is 200 mils of solution. We're going to convert that to liters. So we have to divide by 1,000 mils, and then we're going to multiply by the concentration of the sodium chloride in that solution, which was 0.200. When we do all of that, we'll end up with 0.040 moles of the sodium chloride present in our solution. So now we can use that to do our stoichiometry problem, and that becomes the thing that we have, and the thing that we want is how much of the product, the methyl bromide, is produced. So it looks like this. We have 0.04 moles of sodium chloride. We're going to use the mole ratio from the balanced chemical equation. In this case, it's very simple. It's 1 to 1. And that's going to end up giving us 0.04 moles of methyl bromide. Again, our conversion factor is simply the mole ratio from the balanced chemical equation. All right. Didn't want to spend too much time on this, but I do want to talk a little bit about reactions in solution. And in particular, there are several different outcomes that can happen when we have a reaction in solution, and it's worthwhile to review that. First of all, the simplest and most stupid thing that could happen is no reaction at all. I mean, it's always possible to mix two solutions together that do not engage in a chemical reaction. We could have a reaction where the products all remain in solution and they're effectively invisible. We can't tell that they're there. We can't see anything that's happened. We would have to do some sort of more sophisticated analysis in order to find out if a reaction actually had happened. We could also have some products that appear as solids. Okay, and when you mix two liquids together and a solid comes out, we call that a precipitation reaction, and the solid that it forms is called a precipitate. We could have some products that are liquids that don't mix with the solvent. That is to say, they're immiscible with the solvent. For example, if we have a reaction that produces a hydrocarbon, like an oil or something like that, it wouldn't mix with water very well, so it would separate, and you'd see a clear separation in the solution. We also could have reactions that produce gases, and you'd see the gas bubbling up out of the solution. So there's lots of different things that can happen in solution. I think the thing to be aware of, though, is you may not always be able to observe a change that happens. Doesn't mean that no reaction happened. It just means that those things that were created by the reaction stayed in solution.